This is the moment. Jeff says his game on Sunday, he thinks it's at 7.
Okay.
You feel like playing anything in?
I have this, my brother.
Does he play soccer? Bummer.
Okay, so remember we were talking about error correcting codes last time. Okay, and so today we're gonna. Last time we saw a code where, I mean, remember what's the idea? The idea is that you want a code, and a code is a set of words, something like a dictionary. You only use words from that code. And now I want to send a message to you guys. So I pick one of the words in the code, I send it to you, but then the channel is noisy and it might ruin the word a little bit, and you might get a slightly distorted version of the word. And what we want to do is to choose a code so that you can take your word, which is almost the right word, and be able to figure out what the right word actually was. So last time we saw a very simple example where if you want to send 2 bits, A and B, then you can add a third bit, which is A plus B, the sum. And we saw that that was a way of detecting whether there was one error or not, assuming that there was only at most one error. Okay? So that was an example of a code where you could figure out if there was a mistake, but you couldn't fix it. Okay? And so what I want to talk about today is the Hamming code, which is a nice code which can actually detect an error and fix it. Okay? So our goal for today is to build a code. Leave a space here. To build a code of words in. Let's keep using the alphabet 0, 1. So each word is just a bunch of zeros and ones. Which can detect and correct an error. So we want to detect and correct. And that's what's different about this as opposed to the previous one that we talked about. Okay? And the idea, of course, is that you want a code that has a lot of words, because for a given length, you want to be able to use a lot of different words so that you can have many things that you can say. So the idea is that you want to build a large code consisting of many words, so that you can detect and correct mistakes by using this code. So what's the story of this? Actually, so Hamming was working at Bell Labs, and this was in the 40s. And they basically had these punch card computers, right? And so if they wanted to perform some sort of computation, they would have to put the punch cards into this computer, and then the computer would read the punch cards and then process them in some way and get the output. But the problem is that this technology wasn't so sophisticated, and all the time the computer made errors in reading the punch cards. Okay, and then the computer was programmed to know that there was an error, and whenever there was an error, it would beep and stop. Now the operator would have to go and take the punch card and go back and feed the punch card again, and just like we talked about last time. I could send you a message, and you could either receive it and know that it was correct, or if it was incorrect, you had to tell me, send it again. Okay? But this meant that Hamming had to work weekends, because if you wanted to perform a long computation, and he couldn't have the computer running over the weekend, because all of a sudden on Saturday morning it freezes, and then there's nothing he can do. And so he really wanted to figure out a way of doing this, so that not only did the program detect mistakes, but it could also correct them on its own and keep running. And of course, this is relevant not just with punch cards, but with any kind of error correction. Okay. Now, recall what we said last time, that if you pick a bunch of words that are a distance 3 from each other, then you can detect and correct one error. If the code has distance 3 or more. If every two words differ in at least 3 positions, then one mistake can be detected and corrected. And so what we want to do is basically find a lot of words that are far from each other. Okay? That are a distance at least 3 from each other. That's our goal. So let me make a rough estimate of what we could possibly do. Our words are 0, 1 words of length L. So there's 2 to the L words. Okay. Now, what I'm going to do is I'm going to imagine that this is the set of words. 0, 1 to the L. Okay. So the words are, each word is represented by a dot. And I just imagine that I'm able to represent this in a circle. Okay. Now, the code is going to consist of some of these words, not all. Right? So the code maybe consists of this word, and this word, and this word, and this word, this word, this word. Okay. So these purple guys are the words in my code. Words in the code C. So the purple words are the ones that I'm going to use to send you messages, and the black ones I'm never going to use. Okay? Now, I have a notion of distance, and just like I can define in the real plane, what are the points at distance, at a certain distance from a point? The points that are at a distance 1 from this point are a little circle around. And so let's just imagine that we do that. For each word, let's draw a circle around it consisting of the other words that are at distance at most 1 from it. So I draw a circle of radius 1 around each word. So what does this mean? U is a word in the code, and the circle consists of the words V such that the distance between U and V is at most 1. So it consists of those words. Now, the circle is a visual aid, but really, this circle just consists of those points, the words that are a distance at most 1 from you. Okay. So let me call it a ball to emphasize that it is kind of a full ball. Okay. Now, so this is what I want to say. How many balls are there? Well, I have one word for each word in my code. So the number of balls is the number of words in the code. I should say C is the name of the code that I'm going to build here. Okay. So C consists of the purple dots. There are C balls. Now, how many points are inside each ball? Think about that for a second. here's a word in C. You're going to consider the words that are at distance at most 1 from this one. Which ones are they?
This guy.
Well, this guy is certainly in the ball. It's a distance 0 from it. And then the other ones are obtained by either changing the 0 to a 1, or changing this 1 to a 0, or changing this 0 to a 1. You can flip exactly one of the bits, but you can't flip two of them. So all the possibilities are either, I mean, there's L bits here, right? So either you flip one of the bits, you choose which one, there's L possibilities, or you flip none of the bits, which is 1. So in total, you have L plus 1 words in this ball. There are L plus 1 words in each ball. Okay. And the last thing I want to say is that I drew these balls in a kind of convenient way to not overlap. But I claim that that's not an accident, that they really don't overlap. The balls don't overlap. Why? Well, let's prove it. So, proof, suppose two of them do. Suppose the balls of U1 in C and U2 in C overlap. So that means I have a word like this. I mean, I have a ball like this. I have a ball like this. Here's my word U1. Here's my word U2. And I'm claiming that these balls, I'm assuming that these balls overlap, meaning that there is some word here in the middle. Okay. What does this mean? It means that the distance between U1 and V is at most 1, because V is inside the ball of U1. The distance between U2 and V is at most 1, because V is in the ball of U2. But I said last time that this distance function is actually a distance function that satisfies the triangle inequality, meaning that the distance between U1 and U2 is less than or equal to the distance between 1 and V plus the distance between U and V, which is at most 2. But U1 and U2 are in my code, which means that they are not at distance less than 2 from each other. Because I'm assuming that this is a code that has distance at least 3. Contradicting that the distance of the code is 3. Or greater. Okay. Another way of saying this is, if you can get V by flipping one bit of U1, and if you can get U2 by flipping one bit of, if you can get from V to U1 flipping one bit, and you can get from V to U2 by flipping one bit, then you flip this one, and you get from U1 to U2 by flipping 2 bits, which is impossible. So the balls don't overlap. There are C balls. There are L plus 1 words in each ball. What is the conclusion? The number of balls total, the total number of balls in the code in the big circle, the total number of words, not balls, the total number of words is 2 to the L. The total number of words in this picture. Okay. So this is greater than or equal to the total number of points inside the balls, which is the number of balls times the number of points in each ball. And therefore, what I obtain is this. Okay. So what I just proved to you guys is that if you have a code of length L and distance 3, then this is the largest that it can be. It can't be any larger than this. I just proved that. So if I want to build this error correcting code, one error correcting code on 0, 1 to the L has at most 2 to the L over L plus 1 words. This is the largest code that we could possibly hope for. Okay? And remember, what we're trying to do here is build a very large code, but this is saying you can't get any bigger than this. This is the largest you can hope for. Okay? And so, of course, the next natural question is, is this a good bound? Can I actually get this number of words? Maybe not. My argument was kind of a simple argument. It gave me some bound, but maybe that bound is not possible. So the question I want to ask myself is a code that large actually possible? Does a code that large actually exist? Okay. Okay. So now what do I want to do? Well, for example, for L equals 2, does a code this large actually exist?
No.
It's kind of an obvious reason why a code this large doesn't exist, because if L is equal to 2, this is 4/3.
Right.
You can't have a code with 4/3 words. So let's maybe make our life a little bit easier by just saying this guy is going to be an integer. So to make our life easier, assume that this guy is an integer. Now, when is this guy an integer? Well, you're taking a power of 2 and dividing it by something. So if you want an integer, this something better be a power of 2. So let's assume that L plus 1 is 2 to the n for simplicity.
Why don't you just take the floor of it then?
Well, you'll see why. You'll see why. I'm going to assume L plus 1 is equal to 2 to the n. And let me actually explain to you why. Because if you remember when you first started using a computer and you saw the file sizes were always either 128 or 256 or 512 or 1024. Yeah. File sizes were actually measured in this way. And for example, when they tell you that a file size is 1 kilobyte, what is a kilobyte? Well, this is totally going to throw off any Colombian or anybody who has grown up in a metric system, because in a metric system, this should be 1,000. A kilo is 1,000. But so, of course, you can imagine who came up with the name kilobyte. It was an American. And this American decided that this was 1024 bytes. Or, for example, what's a megabyte? Well, a Colombian is going to think that that's 1,000,000 bytes. And that would make sense, but it's not. It's whatever. 1,048,576 bytes. Okay.
So the closest power of 2 to.
So this is 2 to the 20.
Right.
Just a side note, that's why if you buy a hard drive and it says it's like 10 gigabytes and you plug it in and it actually says like 9 point something, it's because they measure the hard drive space with the actual 1,000, 1 million. And so when you actually measure it using the 1024, it's slightly less.
Oh, I didn't know that. So if you buy a hard drive that says 100 gigs,
Yeah.
and you actually go there, it's going to say
It's just like
99 point something. And you might feel that you were ripped off, but
Yeah.
really, you weren't ripped off. It's just a different measuring system. Actually, something else that I also found teaching calculus last semester is that Americans and Colombians write numbers differently. So you guys would write it like this, but in Colombia we write it like this.
Agreed.
A million is over there. Maybe because we have to deal with more millions because our currencies are weaker. So sometimes you have something like 1 0 0 0 0 0 0 0 0 0 0 0 0. You might lose track, but that's how we write it.
That's nice, actually.
But you guys would just write it like this, and well, depends what you're used to. Anyways, error correcting codes. That's what we were talking about, right? The point is this: that really, computers, algorithms, etc. There's a lot of algorithms that are much easier when you apply them to powers of 2. For example, there are sorting algorithms that if you want to sort a pile of papers, there's an algorithm that says split in half and sort each pile independently, and then sort them together recursively. This is called merge sort. But if you start with a pile of size power of 2, then this is very easy to analyze. If you start with a pile that's size not a power of 2, then when you split into 2, the 2 are going to have different sizes, and it just gets annoying, and the idea is the same. And so that's why in computer science, people often just assume that the lengths of things are powers of 2. Okay? Makes your life easier, and in practice, you can just implement things that way. Okay?
Will power of 3 make 1 easier too? Sorry? Will
Powers of 3 would make it easier than powers of 10, but harder than powers of 2, which actually is also why in computer science a lot of things are based on 0, 1, just because everything is easier that way. So this is for simplicity for 2 reasons: for simplicity of implementation and for simplicity of proving theorems. Okay, we're going to assume that L plus 1 equals 2 to the n. And so the question is there one error correcting code of how many words? Well, word length is, what did we say the word length was? We started with words of length L. So L is going to be 2 to the n minus 1. How many words do I want? I want to figure out if I can get this right number of words. 2 to the L over L plus 1, which is 2 to the n minus 1 over 2 to the n. So that's 2 to the n minus 1. Okay. And I want error correction of 1, meaning I want a distance of 3. Okay. According to this argument, this is basically the dream code that we could. This is the best we can hope for. This is the biggest we can hope for. Okay. So now we're going to think about this a little bit. Word length 2 to the n minus 1. Number of words is this guy. Distance is 3. Now, we said last time that there is one particular kind of codes that we like very much. And that is a linear code. We said linear codes are very good. And so we might even hope that we're going to get this to be a linear code. Okay. Try make C a linear code. If it is a linear code, that means it's just a subspace of what?
F2 to the
Well, my field is F2, right? Zeros and ones. And what is the length of the words? 2 to the n minus 1. So what I'm going to try to do is to build a linear code. In other words, a subspace of F2 to the n minus 1. Well, one thing that you can tell me immediately about a linear code is that being a subspace, how many words does it have? Well, any vector space over F2 of dimension d has 2 to the d words. Right? Because you're just picking d coordinates, and each coordinate is 0 or 1. So if you want a linear code that has 2 to the n minus 1 words, then that really already looks like a linear code, where the dimension is this guy. Okay. If we just pick any subspace of dimension 2 to the n minus 1 of this guy, then immediately the word length is 2 to the n minus 1, and immediately the number of words is the right number of words. 2 to the dimension. Okay. The one thing we have to do is to pick this subspace carefully so that our distance is equal to 3. And it's not clear if you want to take a subspace of this guy, which is a nice choice for a subspace of dimension 2 to the n minus 1. So we're looking for a subspace U of F2 2 to the n minus 1 minus n, no, 2 to the n minus 1 with the dimension equal to 2 to the n minus 1. Well, I don't know. I mean, do any of you have a favorite subspace of this dimension of this guy? It's not so clear, huh? It's not so clear what you should do. But remember that we learned a tool last time of how to build one code from another one. I mean, part of the problem is that this guy has dimension 2 to the n minus 1, and I'm picking a huge subspace. I mean, this is almost full dimensional. Yeah, this is 2 to the n, so if n is 10, this is 1023, and you're picking a subspace of dimension 1013. Huge. And that's part of the problem. How do you pick a subspace this huge of this guy and a natural one? But then this is exactly what we talked about last time, that if you want to build a huge code, then duality lets you build a small code. So instead of choosing U, let's choose the orthogonal subspace U. So instead of this guy, I could choose the dual. And what is the dimension of the orthogonal subspace?
2 to the
Just n.
If you have two complementary subspaces, the dimensions add up to the dimension of your space. So if you want 2 to the n minus 1 to be this plus this, then what you need is a guy of dimension n. And that's much nicer. First of all, it's much smaller. And second of all, it's much cleaner. So now we want or a subspace of this guy, and then you just make U be perp. Okay? So what I want now is to build a subspace of an n-dimensional subspace of this guy. Okay? And I'm going to show you that actually we don't have a lot of freedom here. Because let's say that this, how do you build a subspace? Well, maybe let's pick some generators. Okay? So what are the generators going to look like? Well, you basically need n row vectors of length 2 to the n minus 1. So let's say that this is generated by some matrix. Okay. Now, if this matrix generates an n-dimensional space, then what can you tell me about it? Or
The rows are linearly
the rows are linearly independent.
Yeah.
right. Or
And what is, yeah, or
end of the columns.
n of the columns are linearly independent. How many possible columns could you put here?
What do you mean?
How many different column vectors exist?
And you mean for each spot, like for the first spot,
For a column? I mean,
for any column? Okay.
2 to the n.
Two.
how many column vectors of length n are there?
2 to the
It's
n.
just 2 to the n. Right?
I mean, theoretically, you want one less. You're not going to put the 0 vector in it.
And it seems kind of silly to put a 0 vector. Okay. But I mean, how many choices for a column do you have? Well, you have n entries, and each entry is a 0 or a 1. So there are 2 to the n possible column vectors.
You need them all.
Which is almost what we want. We have one extra, but there's one that we clearly shouldn't put, which is a column of zeros. It's kind of a silly thing to do, because then the first coordinate would never appear in the row space. Okay, and let's just, now there's one that we don't want. We don't really want to use. And so there really is a very natural choice here, which is to put all the other ones. Let's put all the possible column vectors. And so that's what I'm going to do. So in this, I tried to draw this to be kind of 3 by 7. So I'm going to put all the different column vectors of length 3. So I have 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. So these are all the column vectors, all the 2 to the n minus 1 possible column vectors. Okay. And again, there's kind of an obvious reason why you don't want to pick equal column vectors, because if you pick equal column vectors, then in the row space, those two coordinates are always going to be equal. So that's not so interesting. So you really, if you want to do something interesting, you want to pick different columns. You want to pick them not to be 0, and so this is kind of the only natural choice that we have. Okay? And so this is basically what I'm going to hope is the right thing. I hope this is the right thing. So what is U and what is V? V is the n-dimensional guy. It's just the row space of AN. And what is U? U is the orthogonal complement. In other words, the null space. Okay. And so I hope that this works. This is the guy of the right dimension. So what I'm hoping is that this is the code I'm looking for. And that's the theorem, that it is. And this is what's called the Hamming code. Hamming code U is a one error correcting code of word length 2 to the n minus 1, number of words 2 to the n minus 1, and distance 3. That's what I'm going to show. But I hope that I conveyed to you that this is kind of a very natural choice, and that really whenever you want to pick error-correcting codes, really what you want to do is have them come from a natural mathematical structure and kind of let it appear in front of you. And let the mathematics take care of the... I mean, the point is that this subspace is so nice that it's going to take care of the error correction for us and just kind of... Yeah, it's basically going to take care of the distance 3 by itself. And we didn't have to engineer it that way. Okay. So what do we need to show? Well, by construction, the word length is 2 to the n minus 1. By construction, the dimension is 2 to the n minus 1. So that's the right number of words. And so the only thing I have to show is that I have a distance equal to 3. Okay. So let's show that. Let's take two words. U and V in the Hamming code. Okay. Now, again, what is the length of these guys? Well, the length is 2 to the n minus 1. Okay. And I want to come up with a nice way of labeling the coordinates. U is a row vector that is generated by those rows. And so I have a natural way of labeling row vectors of this length. Instead of calling, I mean, if U is generated by this, instead of calling the coordinates U1, U2, U3, and so on, let me take care of this extra structure that I have and call this coordinate U100, call this coordinate U010, call this coordinate U001, and so on. In other words, what I'm doing is calling them 1 through 8, but in binary. So and that's going to be useful. So, you know, U is something like U100, U010, etc. Okay. And I'm going to now. Actually, I'm not going to take U and V to be in U, because remember, for a linear code, the minimum distance is the minimum weight of a word. Remember we said last time that the distance between U and V is just the weight of the word U minus V, which is in the code because this is a linear code. So what I want is that for any guy in U, the weight of U, in other words, the number of non-zero coordinates, is at most 3. 1 to show this. Okay. I want to show that every word has weight at least 3. And so let's do it in steps. First step, no, 0th step. Why is the weight not 0? Oh, well. The 0 word is in this linear code. And it always has weight 0. And so the distance of a code is equal to the weight, to the smallest weight of a non-zero word. Okay. So the first thing is for U not equal to 0, well, if U is not the 0 vector, it has a non-zero coordinate. So the weight is not 0. Okay. Now let's suppose that the weight of a word is 1. Okay. So if the weight of a word is 1, that means that the word has exactly 1 non-zero coordinate. So U is 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Okay. For some coordinate. And let me call this coordinate, again, remember the label of this coordinate. let me keep these lengths. So the length here is 7. Okay. This coordinate is labeled by some binary word. I don't know, maybe 0, 1, 1. Is that what I labeled it? Oh, yeah. Well, I'm going to claim that this is impossible. And the reason is this. Let's go back to the null space of this guy and look carefully at what it is. So I want a row vector that is orthogonal to all of these row vectors. So for example, what is the first equation saying? The first row vector dot u is equal to 0. What that's saying is that u100 plus u110 plus u101 plus u111 is equal to 0. That's what the first equation says for u to be in the null space of AN. The second equation says u010 plus u011 plus u110 plus u111 is equal to 0. And the third equation says u001 plus u011 plus u101. u111 is equal to 0. How did I do that without looking? How did I write these equations without looking at this matrix? It's not magic. There's a very simple way.
You picked up all the vectors that had a 1 in the first spot, and then all the ones that had a 1 in the second.
The first equation involves the guys that have a 1 in the first position. Second equation has the ones that have a 1 in the second position. The third equation has the ones that have a 1 in the third position. It's precisely because these guys have a 1 in the first position, these guys have a 1 in the second position, these guys have a 1 in the third position. So these are the conditions that you need to be in the null space. That the summation of u1 star star is equal to 0. The summation of u star 1 star is equal to 0. The summation of u star star 1 is equal to 0. So how can you have a guy like this which has only one non-zero entry? Well, if u is in the null space, then the summation of u star 1 star is equal to 0. But it's actually equal to 1 according to this, because there's only one coordinate with a 1 here involving a 1. So u is not in the null space. So that's why you don't have words of weight 1 in this code. So 2, let's suppose that I have a word of weight 2. Okay? So any word like 0, 0, 1, 0, 1, 0, 0. Okay? And I look at their labels. So they happen to be 0, 0, 1 and 1, 0, 1. Okay? But this could be any two words, but they're different. Okay? Because they're different, what can I do?
We disagree on one of the ones.
If they're different, they have to disagree somewhere. So I'm going to pick a coordinate where they disagree. And look at this equation. Summation of u, that coordinate, the other ones. What is that equal to? Well, these two guys disagree in that coordinate, so one of them has a 1, one of them has a 0. So one of these ones appears in the summation, one of them does not. So this is 1, which means that u is not in u. So the weight of a word cannot be 2. At this point you might wonder, can I also prove that WU is not 3? Well, first of all, before I say that, let me just say I'm done, right? I'm done because I showed that the weight is not 1 and it's not 2. So it's at most 3. Now, can the weight be 3? Well, it can. Give me an example.
First, like 1, 0, 0. So put u is 1, 0, 1, 0, 1, 0, 0.
Okay. So how did you pick these, Kim?
That's 1, 0, 0.
This guy is 1, 0, 0,
It's 0, 0, 1.
0, 0, 1,
And that's 1, 0, 1.
and this is 1, 0, 1. Okay. So Kim picked these so that in the first coordinate there's exactly 2 1s. In the second coordinate there's all 0s. In the third coordinate there's all 1s. And so therefore the summation of u1 star star is 1 plus 1. The summation of u star 1 star is nothing. And the summation of u star star 1 is 1 plus 1. Okay. And so this is why at 3 this argument that we made breaks down. But this is good because it should break down, because this is really kind of the optimal code that we can build, and it's unrealistic to hope that it'll be able to correct more than one mistake when the bound that we got here was absolutely tight. So there's no hope that this is going to do any better than what we hope it will. Okay. Okay.
Sort of optimistically hopeless or something.
Yeah. So that's that. That's the Hamming code. It's an actual code that can correct mistakes. You can use it in practice. Let me just very quickly say something else, which is that we talked last time about this McWilliams relationship. Between the weight enumerator of the code and its dual. We saw that there was an equation relating them, which said that if you can find one, you can find the other one. Okay? It might be a little bit surprising, but actually here, it is easier to find. One of these is very small, one of these is very large. But it turns out that they... Oh, no. I'm about to say nonsense. But what I said last time is that if you want the big one, then very often you want to just compute the small one and compute the dual. Well, here we have a small code which is V. Okay. And this is an exercise. And an exercise that I'd really like you to do, because it's a very simple answer. And then you can use it to find the weighted enumerator of u, which is a very good thing, because we said that this is the guy that allows you to compute probabilities of whether your decoding algorithm works. So if you're going to use the Hamming code in practice, then you want to have a good handle on how it performs. And this allows you to do that. So this is a very nice piece of applied mathematics where really you really do need the mathematical structure of vector space over the field F2, and it just kind of takes care of error correction for you. All right, stop there. hours?
I'm not going to switch right now. No.
Not outside of that.
I want to go home.
You're kind of like,
But I know you can do algebra, so French.
I saw that your algebra 1 and 2 is kind of
Yeah, Tom got like a one-line proof for Oh,
I'll be there.
I was like
Probably
the
at
first
some
one.
point.
Yeah.
first one was like
I'm
3
supposed to have
lines
office
for
hours.
2 lines.
Yeah, I haven't even, I looked at the whole, like what problems were assigned yesterday. So I haven't actually done
You say the lecture today helps. That's where you have a 1 line proof for the number 2 from the lecture today because it's that short sequence of simplicities.
That's cool. Okay.
Especially
Yeah, I haven't even read it. So.
I guess that's also. Yeah. So I guess there's several good reasons. Maybe maybe it just happened that they started that way because they had it on and off, and then they started realizing that actually it's a very handy thing to do.
But if I do go home,
Because a lot of these houses are really.
if I do go home, well, then I'll really have
You don't want to use it as
Friday
power to.
finish it. I am not waiting until Sunday again. So. All right. So I think I'm gonna have lunch and then I'll
Yeah, I
decide.
might-
So
I'm not sure.
maybe you'll see me, maybe
I
you
don't know
won't.
anything.
Bye, Miranda.
But I just.
Bye, Jeff.
That was a long time ago.
Yeah.
So I wonder if
Yeah, I'm not sure. I mean, the part that I know about more is the algorithm. And there, I know that all the time, you're analyzing an algorithm, and it turns out the answer is log at base 2 of the algorithm. So it's just very natural to have inputs that are powered into. I guess just because it's so often, I guess really what it is it's so often in life, you want to take a task and split it in 2. Whenever you do that, it kind of naturally gives you a tree that branches out and branches. There's 2 different branches.
no, what you think, so maybe, did you do the other kind of thing?
Not always, but
No, I know, yeah, I was just thinking about that, you know, that's sort of like a natural phenomenon, like that, you know, those, the numbers, like the Fibonacci or something, or like, you know, exponential.
yeah.
Yeah, yeah.
Or a variable.
Is there something special?
Like kind of 2 is like on and off or greater than less than.
Yeah.
Yes or no?
Yeah, for example, that so when you do any algorithm involving real numbers, it's very natural to split which one of your 2 real numbers is it. So when you're doing sorting algorithms, I think that's part of the reason is to pick one and